So now that we know how to convert a rational function from one form to another, that means we can start to look at a graph of a rational function, because we know that we need to have it in this form in order for us to really understand quite a few things about this curve. So the first thing to know is that when we graph a rational function, it creates a special type of curve called a hyperbola. Okay, so whenever you graphed a second degree polynomial, you ended up with, or a quadratic function, you ended up with a parabola. So whenever we graph a rational function, we end up with something called a hyperbola. On our hyperbola, on our curve, the lines represented by x equals h and y equals k are called our horizontal and vertical asymptotes. And this is actually backwards because this one is vertical and this one is horizontal. And an asymptote is basically a line on your graph, or it's not really on your graph, I guess we could say it's an invisible line that our curve is approaching but will never actually touch. So an asymptote is something that shows that for the specific type of function, but you'll also see it later on if you continue to study mathematics. And the intersection point of our two asymptotes, so the vertical and the horizontal, is called the center of the hyperbola. So the center of our hyperbola, and its coordinate is h comma k, so h and k. Now, if you guys remember from our square root function, that point h and k was our vertex of our function. It was the start of our graph. And for the absolute value function, it was again the vertex. For a rational function, h and k, that point h and k, is actually not on our curve. It's the center of our curve. And we're going to look at what that means in a second. So it's important to know that this point h comma k is actually not on our curve, but it is important for us because we'll use it later on when we solve to find the rule. So let's say we have a graph like this. This is a graph of our function f of x, where f of x is 3 over x minus 1 plus 2. So this is my value of a. Positive 1 is my value of h, because we remember the form is x minus h, and 2 is my value of k. So I said before that we have an asymptote. We have this line at x equals h. In this case, h is 1. Now I'm going to attempt to draw a straight dotted line here. Woo, that didn't go well. Anyway, so that's my line x equals 1, or x equals h if you want to be very general about any hyperbola at all. We can also draw a line at y equals k. In this case, k is 2, so we can draw another line at y equals 2. Whee! Okay, so y equals 2, and again, if we want to be more general, we can say that y is equal to k. And where these two lines meet, that's our coordinate h comma k, but let's be specific for this graph, and we'll say that it is 1 and 2. And we call that the center of our hyperbola. So it's the center of our curve. And you can see that it's actually not a part of our curve, because our curve is this sort of scoopy shape on either side. So that's one part of it there, and this is another part of it here. And like I said, these lines that I've drawn on are not actually a part of our curve. Our curve is always approaching them in either direction, but it will never ever reach. So if I were able to zoom out farther and farther, we would see that our curve would always be approaching, so this will get closer and closer and closer as you go up farther, but it will never actually touch x equals 1. So let's think about y. If we use the value of x equals 1, and we were to plug it into this function here, so we would have 3 over 1 minus 1 plus 2. And this is the problem right here. If we have 1 minus 1, that gives us a 0. If we have a 0 on the denominator, it's actually undefined. So our curve cannot exist at this x equals 1, because that is undefined for this function. So we actually cannot have a point at x equals 1. So that's why our curve ends up being shaped the way it is.